Hello, welcome to the Lab of Physics 143, Physical Systems. Today you are going to explore the force of a spring. As a physics superhero, you can use your knowledge in science to make useful gadgets to help you in your task of defending the world from supervillains. One interesting device that can improve your achievements is a spring. You are considering to include springs in your standard equipment. For example, it can help you to measure masses, which you might need to know in your search for peace. Before you begin your designs, you want to explore in detail various aspects of spring systems. When you apply a force to stretch a spring, there is a force made by the spring that tries to pull the spring back to its original length, to what we call the equilibrium length. The same happens when you compress the spring. There is a force that tries to push the spring back to its equilibrium length. This type of force is a restoring force, and you can find it also in rubber bands or any elastic object. This force opposes to the deformation of the spring, and it is proportional to the deformation. This mathematical expression describes the force made by the spring. F is the force of the spring, x is the displacement of the end of the spring, and k is a proportionality constant. This negative sign indicates that the force opposes the displacements, goes in opposite directions. This equation was introduced by Robert Hooke in the 17th century. This expression tells us that the longer the deformation, the longer the force. The constant of proportionality k is characteristic of each spring. Can you tell in which units we measure this constant? If you apply different forces or if you hang different masses, you can determine experimentally the constant of the spring. Be aware that the force does not depend on the physical length of the spring, but on the displacement of the end of the spring. If you characterize well one spring, you can use it to measure weights. This is what a dynamometer does. It has only a spring inside. If you hang on a mass at the end of the spring and you apply a small force to it, the spring will oscillate, and the frequency of the oscillation will depend on the hanging mass and on the spring's constant. Because measuring the frequency of this oscillating spring is not easy to measure, you are going to use a data acquisition device. This force sensor measures the force applied to it, for example by the spring. It sends its value to this electronic device, which then communicates with the computer. The software records the actual value of the force and plots, in real time, the force versus the time. With this data, you can measure the period of the oscillation and the frequency. You only have to run it and then analyze the data. For any periodic oscillatory motion, just as the spring, you can describe the position of the object by this equation. Where a is the amplitude, the maximum distance that the extreme of the spring is going to achieve, f is the frequency of the movement. If we want to calculate the velocity, we know that we only have to derive this expression. If we derive it with respect to time, we get the velocity, and then we get this minus 2 pi fa times the sinus of 2 pi ft. And if we derive it again, we obtain the acceleration. The derivative of the velocity with respect to time, we have minus 4 pi square f square a cosinus of 2 pi ft. So this is the acceleration. And if we now compare this with Newton's second law, which tells us exactly this, it's an exercise for you to compare this expression, this other one, and this last result to obtain this. And from this you can get that the frequency is equal to 1 over 2 pi, the square root of k divided by m. So you can get the frequency of the movement by just characterizing the spring and knowing the mass that is moving. Knowing this, you can measure the oscillating spring and determine the constant of the spring by just measuring how it is oscillating. In this lab, I want you to measure the elastic constant of one spring with two methods. The static method of hanging the different masses on a spring and the dynamic method of having the spring oscillate. Also, you should explore another aspect of the springs that you choose. You can determine how the period of the oscillation changes if you have springs connected in series or in parallel. You can determine the effective constant of two springs connected in series or in parallel also. You can explore the energy stored in a spring system or study how friction makes the system lose energy. Also, all I have mentioned is assuming that the mass of the spring can be ignored. You can test the validity of this approximation, or you can think of something else you consider interesting in this physical system. And remember, don't forget to write everything you do and may the science be with you.